Right, we are starting chapter 23. Last chapter was over electrostatics. This chapter is over electric currents. This is covering pages 436 to 439. All right, so let's start with a flow of charge. Well, what is a flow of charge? Flow of charge is another way of saying electrical current. I want you to think about what an electrical current is. When we plug a device in and we're wanting to get an electrical current through it, what we're wanting is for charge to flow through it. So what does it take to get a current to flow? Well, to get that idea, let's think about back to chapter 15, where we're talking about heat transfer. What has to exist in order for heat to transfer from one object to another? There has to be a difference in temperatures, right? So you have to have an object that is hotter and an object that is cooler, and when they touch, that heat is going to flow from the hot to the cold. Well, the same thing has to happen in order for an electrical current to flow. You have to have a difference in electric potential. So you have to have one end where you have high potential and another where you have low potential, so you can push that charge on through. So you have to have an electric potential difference in order for an electrical current to flow through. So when we think of electrical current, we want to think of it as being like a line of electrons inside the wire, and they're moving from the wall, and the little electrons go through your device and turn it on. But it's not actually the electrons that are moving. In fact, they move very, very little as far as a migration of spots. They kind of like to stay in their spot. So it's more like they're students in a line, and they're passing the charge along from one student to the next. So it is their electrical fields that are oscillating and vibrating and disturbing one another that's passing that charge on, rather than the electrons themselves. Now, especially in an AC current, we'll get to that, electrons don't really move from place to place. There's no net migration. Inside a DC circuit, you might have a little bit of movement, but even then, it's still going to be the electrical fields that are causing the current to flow. It's like they're passing the charge from one to the next. So that rate that they're passing is called an ampere. It is abbreviated with a capital A. And then 1 ampere is like 1 coulomb of charge per second. In the last chapter, we talked about how a coulomb was the electrical charge of an electron. So 1 ampere is 1 coulomb being traded per second, which is pretty small. So don't generally find electrical devices that have 1 amp. They're usually like a lot more than that. Now, one interesting thing to keep in mind is that if you have a wire that is carrying a current, it is 0 charge. The wire itself is not charged at all. The wire does not become a huge negative conductor. It's just a wire. Now, the thing is that you can collect the charge off of that wire, so that's why it's important to be for the wire to be covered or to be grounded. So what provides the electrical potential difference is an electrical pump, or we're just going to call it electrical pump. It's really just voltage, all right? So a generator is usually used to create that potential difference, and then batteries are used to create that potential difference in order to make it so that you can push the charge on through the conductor. So what happens actually is the voltage source, you'll notice if you've looked at a battery that they have a positive end and a negative end. What they do is they pull the charges away from each other, creating that potential difference so that the charges want to complete the circuit and get back together. So in a battery, this is usually done, there's chemicals inside the battery, and when the chemicals are having their reactions inside, it's pulling the positive and negative charges away from each other, so that the negatives are wanting to get back together with the positives and complete the circuit. Now, in an automobile, they don't usually, you have the battery that's use the battery, but they also use a generator inside, and they are using electromagnetic induction, which we'll talk about in a couple of chapters from now, in order to create that change so that your car will work. So the unit for potential difference is volt. You probably could have guessed that already, because when we talk about batteries, we're talking about like a 9 volt or a 6 volt. So potential difference is going to be your volt. Your charge flow is going to be your amps. So those are important. So the current itself is amps, and the battery provides the voltage. And the voltage is what is going to make that difference in electrical potential so that you can have a current flow through. That's why a wire without a battery isn't going to have a current flowing through. It's because there's no potential difference. That wire feels the same all the way through the wire. There's no difference, and so it doesn't need to charge to flow through it all. All right, so in order for a current to occur, you have to have potential difference, and you have to have a voltage source because you can't push them otherwise. So kind of think of it like our hallways as being the conductor, and we have a line of students down the hallway, and we have to get an object from one end of the hallway to the next. There's no way to move through the hallway. We just have a line of students. So the potential difference would be that I have the donut and I need to give it to another teacher at the end of the hallway, and I need that donut to be passed down the line, right? So the potential difference is I have something that they need, and the voltage source is going to be me giving it away and pushing it. Okay, and so everybody has to do their part, pushing. Maybe that's where yelling at each other. You got to pass it. So that's what a current has to have. You have to have potential difference, which is provided by your voltage source to pump through the current through the wire. So keep in mind that charge flows through the wire and voltage is pressed across it. So the charge is what's going in the circuit, and the voltage, you push that across the top of it to say that we're making it move. Okay? So don't ever say that voltage is flowing through the circuit, because voltage doesn't flow. Charge flows. All right, so we've got our wire, we've got our voltage source, and so we've got some current flowing through. The other thing that we've got going on in there is going to be electrical resistance. Every conductor has some resistance to the flow of charge. Depends on the size and the material, how much resistance is there, but everybody offers some resistance to the flow of charge. Resistance is measured in ohms. This is a Greek letter. It's the Greek letter omega. Kind of looks like a horseshoe there, but it says it's pronounced ohm. So thick wires are going to have less resistance than thin wires. Imagine the hallway as the electrical conductor again, and we're carrying something through. Is it easier to walk through that hallway when it's wide or when it's narrow if there's a whole bunch of people? The wide one is going to be easier to walk through than the narrow one. Our hallway gets really, really packed there right in between classes. You've got everybody at their lockers, and you've got double row of traffic trying to go through. You add little kids, makes it quite a mess. So the thick wires are going to be better than thin wires, or have less resistance, rather. Short wires are going to have less resistance than long wires. That should just make sense. If you're desperately trying to get to your class on time with your homework, right, because you've got to turn it in and not get a 0, the shorter the way you have to go, the more likely you're going to get there in time than a long way. So a short wire has less resistance. There's less stuff for your electrical current to encounter. And then just in general, copper has less resistance than steel. That's why copper is often used in wiring as one of the cheaper metals that you can use for wiring that has low resistance, so that you're not likely to burn out your battery or mess up your electronics when they just use a lot of copper. So for most conductors, this isn't for all of them, when you increase temperature, you increase resistance. So if it's getting hot, it's going to resist even more. And the more it resists, the more it's going to increase temperature. Now I say for most, because there are a few metals out there we've talked about in the last chapter about superconductors, where if you increase your temperature, you're going to decrease your resistance. But for most conductors, if it's hot, it's not going to work as well. There is a quiz today. Go ahead and click on the link and finish the quiz, and I'll see you in class.